It is fair to say that curves are a critical part of the railway, and that makes their design, and knowledge of it, fundamental for track designers and engineers. When was the last time you saw a dead straight railway that didn't have a single curve? In this video, we are going to explain the basics of curves and their design. You can expect to learn the key elements of longitudinal alignment, the types of curves you can expect to encounter, the difference between equilibrium and applied cant, the influence of speed in curve design, the important design limits, the factors influencing the choice of cant to apply, how to design a transition for different curve types, and finally what we do when a transition doesn't fit. You can see this is a jam-packed video full of great information, so let's get started. As always, we welcome your thoughts, experiences, and questions in the comments section below. So don't hesitate to share your knowledge or ask any questions that you may have. We're eager to hear from you. When a railway is designed, its course from the start to the end is plotted. This course can be influenced, or in some cases dictated, by the topography of the land through which it travels or by natural obstacles the route encounters. Track engineers need to be able to avoid these obstacles and features. This is where alignment design comes in. The longitudinal alignment refers to the horizontal layout, or geometry, of the railway. It is made up of three basic elements. First and most basic of the three, we have straights. As the name suggests, these sections of track are straight, normally with no cant applied. These sections of track are the fastest parts of the railway, similar to straight sections of road. Ideally, all railway would be designed straight, but this is not practical in the real world. Next up is circular curves. These curves have a constant radius along the length of their arc. Curves are used to change the direction of the railway. They can vary from tight radius, short curves in built-up suburban areas, to long, larger radius curves on high-speed lines. Lastly, we have transition curves. Transitions are in reality a spiral, known in maths as a clothoid. They have a constantly changing radius. Transitions and their use is important for the comfort and safety of passengers. We will look at this in more depth later in this video. Before we dive further into curves, it is worth taking a minute to understand what is meant by the handing of a curve. This is a term that you may hear often, and for your understanding it's good to know from the start. The handing of a curve is simply a way of describing the direction it deviates from the straight. For example, a right-hand curve moves away to the right-hand side of the centerline. Perfect. So now we know the basic elements of longitudinal alignment, we can see how they can be combined as part of a longitudinal alignment design. There are a number of different types of curves, so let's have a look at them. The most basic combination of the elements we have just looked at is the simple curve. The simple curve is comprised of two straight sections that are joined by circular curve of a constant radius. The most common type of curve are transition simple curves. Transition curves have a transition designed either side of the regular circular curve. This allows a smooth build-up of cant, as well as the tightening of the radius, until they match those required for the regular circular curve. This gives a smooth and comfortable ride for the passengers. We will take a longer, more in-depth look into transitions and their design later in this video. The last two types of curves are slightly more complex. In fact, you might hear them referred to as complex curves. A compound curve consists of two or more circular curves with the same handing but different radii. The two curves follow each other in series, separated by a transition. Lastly, we have the reverse curve. A reverse curve is similar to a compound curve, but the curves have different handing, therefore reversing the direction in which the train travels. They can look like an S when drawn out. There are also transitions, too, in fact. Before we start looking at the design of curves, we need to introduce you to some track geometry terms you may not have heard before. These terms will be mentioned a lot going forward in this video and are important parts of curve design. First up is cant. On the railway, cant refers to the difference in height between the two rails. It can also be referred to as super elevation in some countries. This means one of the two rails has been lifted above the other. The outer rail on a curve will be the higher rail. This is known as positive cant. Cant can be negative, but we won't need to know that for this video. Cant is applied to the track to manage the forces on the train as the train goes around a curve. In the equations used for track design, cant is represented by E. Equilibrium cant. Equilibrium cant refers to the amount of cant required for a specific curve radius and train speed, such that the resulting force on the train is perpendicular, or at a right angle, to the plane of the rails. In other words, it is the amount of cant that balances the centrifugal force on the train and prevents it from derailing while traveling around the curve. It is also known as EQ. The equilibrium cant for a curve is calculated using the equation EQ equals 11.82 v squared over r, where the equilibrium cant is EQ, the curve radius in meters is r, and the speed is v in kilometers per hour. Please note this equation is for UK track gauge of 1432 mm. Next, we come on to applied cant. If equilibrium cant is the ideal amount of cant for a curve, so the train is balanced, the applied cant is the actual amount of cant designed and installed for the curve. This will normally always be less than the equilibrium cant. We will look at the reasons why we don't simply apply the equilibrium cant later in this video. Our last term to introduce you to is cant deficiency. Cant deficiency is the difference between the equilibrium cant and the applied cant. It is given the letter D in equations. This is calculated by simply subtracting the applied cant from the equilibrium cant. That is a very quick summary of cant and its associated terms. Cant is a fundamental principle of track engineering and design. We have a great video explaining everything about cant and would strongly urge you to give it a watch if you haven't already. Click the link in the top right corner or in the description below. Also, please hit the subscribe button, so you don't miss out on any of our upcoming videos. Within track design, there is a relationship between curve radius and train speed. This relationship is important for two reasons. Firstly, safety, ensuring that trains can travel on the track safely is fundamental. Secondly, and possibly sometimes missed, is comfort. Passengers don't want to feel like they are on a roller coaster when traveling on a train. Equally, cargo being transported by freight should not be thrown about by a rough ride. As a train travels around a curve, the forces on the train change compared to when it's on a straight. On a straight piece of track, the main force is the mass of the train, that acts directly downwards. On a curve, more forces are introduced. The first force is centrifugal force. This pushes the train outwards on the curve. Importantly, it also acts on the passengers or cargo in the train, a key factor for ride comfort. The second force is the one required to rotate the train around the curve. These are also known, helpfully, as guiding or steering forces. Applying cant to the track helps to both negate the effects of the centrifugal force on both train and its passengers. This is done by shifting the resultant of the forces towards the floor of the train. It also reduces the outward, or centrifugal force, which in turn reduces the steering forces. The steering forces act through the rails, so can cause rail defects and wear, hence why it is important to reduce them as much as possible. If we bring up the equation for equilibrium cant that we looked at earlier, we can see the link between equilibrium cant, train speed, and curve radius. A note on units here. In this video, we will be working in metric units. Sorry USA. Speed is in kilometers per hour, curve radius is in meters and cant is in millimeters. From this equation, we can work out a number of things, depending on what we know. for example, can find out the maximum speed a train can travel on a curve, if we know the radius and cant values. Getting the design of a curve wrong can have major consequences. At the top end is trains overturning and derailing, leading to potential loss of life. At the other end of the spectrum, it can lead to an uncomfortable ride for passengers. While this could be overlooked, fare-paying passengers are the end user of the railways, and their experience does matter. With this in mind, the standards imposes limits on a number of different factors, such as cant, radius, and cant deficiency. These ensure the safety and comfort of trains and their passengers. In the UK, they are leveled into normal, maximum, and exceptional. All designs should be to the normal design limits. Maximum and exceptional limits can be used, where the normal design limits cannot be met and agreement from technical authority is given. This is most likely to happen when undertaking a renewal of a section of track, where the ability of the designer to make big changes is limited by the existing footprint. For the remainder of this video, we will use, for our examples, the UK values that are correct at this moment in time. Remember to always check standards, as they can change over time and vary from country to country vastly. They can also be different for different track types. For example, between jointed and welded track or plain line and S&C. Some of the key limits from the tables are: for cant, the normal design value is 150 mm, while the maximum is also 150 mm. The exceptional value is 180 mm. For the value of cant deficiency, it is split further, with the way the track is constructed being a factor. On jointed track, the normal design value is 90 mm, and the max is 110 mm. When it comes to continuously welded rail, or CWR, the normal is 110 mm and the max is 150 mm. As well as these values being limits, they can also be used to determine what a curve designed to these figures would look like. For example, if we take the equation used to determine the equilibrium cant, rearrange it, it can be used to work out the max speed for that curve, as we showed earlier. We also need to substitute the equilibrium cant for applied cant and cant deficiency. This comes from the fact that equilibrium cant is equal to the applied cant plus the cant deficiency. This gives us the equation max speed, Vm, equals 0.29 times the square root of the radius, times the applied cant plus the cant deficiency. It is easier to show a worked example here. Let's say we have a curve of 1000 meter radius, that is welded rail, and also has an applied cant of 70 mm. For this curve, we need to know the max speed that could be done around the curve. Let's use the equation. So we would have 0.29 times the square root of 1000 times 70 plus 110. The 110 mm is the normal design value for cant deficiency for welded track. This gives us 123 km per hour, or 76 mph as the max speed for the curve to normal design values. Using these design values in the equations helps the design process by allowing the designer to determine the design limits of various parameters. With this information, the designer can work within the calculated values to create an effective design. This is particularly useful when looking at the length of transition curve required. We will cover this later in the video. We have mentioned applied cant a fair amount so far in this video. But, while we have covered how to calculate the equilibrium cant, we haven't discussed much about applied cant. Choosing how much of the calculated equilibrium cant to actually apply to the track is an important decision. Traditionally, the rule of thumb used to be to apply 2/3 of the equilibrium cant as the applied cant. However, thoughts on this have evolved, and now a more nuanced approach is taken. Higher levels of cant deficiency are now considered to help reduce railway rates and are the route favored. Equalizing the applied cant and cant deficiency does have the advantage of allowing the shortest transition length. A range of factors are considered. The train traffic mix through the site is the main one. The track might be designed for higher speed passenger trains, but the majority of trains traveling through the area could be freight trains going at a lower speed, for example. If the area is near a station, the majority of trains might be stopping, rather than going straight through at full line speed. How the signaling arrangements affect the pattern of train movements is another area to consider. Are trains brought to a stop frequently, waiting for a green signal, for example? The cant applied to track, and therefore the forces at play when trains traverse a curve, also have an impact of the track components. Side wear, rolling contact fatigue, and plastic flow are all examples of rail defects that can be caused by bad choices of cant. You can see that there are a number of real-world factors that affect choosing an applied cant value when designing track. It is not straightforward, and draws on the knowledge of the designer or engineer. Knowledge of the operations in the area, as well as the balance of traffic, is key. It can be seen as a balancing act. Ultimately, the track has to be designed to be traversed safely and comfortably at the published line speed. However, through the selection of applied cant values, the track can be optimized for the local usage conditions. This will drastically improve the life of the rails and other track components. So, we have mentioned them a few times now in this video, so let's get onto transition curves. As we said earlier in this video, transition curves are placed either side of regular curves, to smoothly change both the cant and the radius. This ensures a smooth ride for the train, as well as ensuring no sudden increases in the forces acting on the train. In mathematical terms, a transition curve is an example of a clothoid, a type of spiral. A clothoid's distinct feature, or property, is that the curvature at any given point is proportional to the distance along the curve from the starting point. Simply put, it starts off straight, but as you go along the curve, it starts to bend more and more. Imagine drawing a line that gradually bends more as you go along it. This gives smooth curves, perfect for transition curves. Clothoids can also be found in the design of roads and roller coasters. A key property of any transition curve is its length, given that it is over this distance that the changes in radius and cant are made. This in turn brings us to two new terms that will be main aspects of transition curve design. These terms are the rates of change of cant and cant deficiency. These are the rates at which cant, or cant deficiency, increase, or decrease, in millimeter per second of travel, therefore are related to the maximum speed of trains on that section of track. So a shorter transition will naturally have higher rates of change, as the cant and cant deficiency have to be increased or decreased over a short distance, or faster in other words. As with other parameters we have already covered, there are limits within the standards on both of these. As you can see, the limits for both normal and maximum rates of change are the same, but there is no exceptional limit for rate of change of cant deficiency. The higher maximum level of 70 mm per second is for modern CWR. We will use the 55 mm per second value for ease in this video. There are two ways these values can be used. Either calculated values of rates of change can be compared to them, to check compliance, or the designer can use the values to determine a desirable and minimum length of transition. It is worth noting here that transition lengths have to be looked at for both rate of change of cant and cant deficiency, with the greater of the two calculated lengths being used. The equation in its two different forms is shown, one for rate of change of cant and one for rate of change of cant deficiency. They are both arranged to solve for the transition length L. The triangle before E, which we know is cant, is called delta and is used to signify change in. As we have also already seen, V is train speed. For this video, we will not show how they are derived from first principles. Using these equations is best explained with an example. Let's say we have a curve of 1000 meter radius with a line speed of 120 km per hour. The curve has 110 mm of cant applied to it. We are looking at the length of the transition between this curve and a straight. First things first, we need to work out what our cant deficiency is. To do this, we calculate the equilibrium cant using this equation. This gives us an equilibrium cant of 170.6 for millimeters. With our applied cant being 110 mm, our deficiency is 60.64 mm. Let's say the current design has a transition length of 85 m. Is this length of transition acceptable? Let's take the equation, arranged to give rates of change. Let's first assess it for rate of change of cant. You can see that the change in, or delta, E, or cant is 110 mm. This is because there is no cant applied to the straight and 110 mm cant on the curve. So our rate of change of cant is 43 mm per second. This is above the desirable, or design limit, of 35 mm per second but less than the maximum of 55 mm per second. Now let's run the same check for the rate of change of deficiency, although we can tell this will be less, as the value of change of cant deficiency is less than the value of cant. Our change in cant deficiency is 60.64. As you can see, it has come out as 23 mm per second. So 85 meters is an okay length for this transition. Say the designer was looking at options to change the geometry of the track here and wanted to look at their options around the length of transition. If the equation is rearranged back to determine L, our transition length, we then need to input values for the rates of change. This is where our design limit values come in. By using the 35 mm per second, the normal design value, in the equations it will give a desired length of transition. If we used 55 mm per second, the maximum, it would give the minimum length the transition could be. Again we have to use both the cant and cant deficiency equations and take the greater length in each instance. As we said earlier in this section, for our example, the cant is the larger change. This will be the limiting factor for the transition length, as is evidenced by the larger L values. So let's plug in our numbers to the cant-based equations and see what we get. We can see that the desirable length of the transition is 104.75 meters while the minimum length is 66.6 meters. The designer now has a range within which to work. This is important as other factors, such as the vertical alignment design, placement of S&C or other assets, as well as local topography, can also influence the horizontal design. But what happens when we start to look at our more complex geometry, compound and reverse curves? If you remember back to the first section, these are curves leading to other curves, either with the same or opposite handing. The theory is the same, but requires the small change in that we have to factor in that the first curve will have cant, unlike our straight, and we are moving from one radius to another. So how do we do this? We have modified our original formula. As a reminder, we previously used delta E to represent the change between the two cant values. In our example with a straight, the applied cant was the only value, as we started from 0. However, now we need to calculate the difference between the two values. To accomplish this, we can use E1 and E2 as variables and subtract the smaller from the larger. This is the essence of what the delta symbol means. The same approach applies to cant deficiency. We can then calculate the desirable and minimum length of the transition between the two values using the same process. When analyzing reverse curves, where two curves are handed differently, we need to add the two cant values. This is because the cant will be applied to different rails. On the left-hand curve, the higher rail will be opposite that of the right-hand curve. To transition from the cant on the left curve to that of the right-hand curve, we need to remove all the cant, go through a flat or zero cant section, and then build the cant back up on the opposite rail. Another way to understand this is to treat the cant on the first curve as positive, and due to the change of high rail, the second cant must be negative. So, a minus and a minus equals a plus. The other point to note, when working with reverse curves and transitions, is the point known as the reverse point. This is the point at which there is no radius or cant on the track. From this point, cant and radius is increased, but in the opposite direction. It's important to note that the rates of change on a transition need to be the same either side of the reverse point. For this to be true, the reverse point should be in the middle of the transition length calculated through the formula. Shall we look at an example of both of these more complex curve types? For these examples, we will just look at a desirable length, so using 35 mm per second for the rate of change. Let's go back to our curve from our first transition example. Here are the values from earlier. Let's say it leads into a tighter curve of 800 m radius with 130 mm cant. We can quickly calculate the equilibrium cant of this second curve. From this, we can get the Cant deficiency. From the figures for both these curves, our change in cant is going to be 130 mm minus 110 mm, giving a delta E of 20 mm. If we repeat, for the Cant deficiency we get a delta D of 22.12. Already, we can see that the rate of change of Cant deficiency will give the greater length transition, as the magnitude of the change is larger than that of the change in cant. Let's take the delta D values and put it in our transition length equation, with a normal design value for rate of change of Cant deficiency. So from the below calculations we can see that the transition should be 21.06 meters in length to be to the desirable design limits. Let's say then, that the 800 meter curve was actually right-handed, making this a reverse rather than compound curve. So, as we said, we now need to add the values together to get our delta values. So for the delta E, we get 240 mm and the delta D, 143.4. Again, from these values, we can tell that the rate of change of cant is going to drive the overall transition length as it has the bigger magnitude of change. So let's run the equation. A transition of 228.57 m would be needed. Within this transition, there would be a reverse point at halfway, so 114.285 meters in. As you can see, I have only calculated one of the rates of change for these examples. Please ensure you do check both rates if doing design work, to ensure nothing is overlooked. But what happens if you cannot fit in a transition? In areas that are constrained, or have complex geometry, such as S and C, it is not always possible to fit in a full transition. In these cases a virtual transition can be used. A virtual transition, or VT, is an instantaneous change of geometry with no transition length. VTs are still governed by the same limiting values as normal transitions. But in all the calculations we have done so far, we need a length to be able to check what rate of change we are getting, right? We cannot use 0 because multiplying by 0 gives 0 and dividing by 0 gives us an error. So what length do we use? The answer is 12.2 meters. Why 12.2? It is the distance between the bogie, or wheel sets, centers of a Mark I coach used by British Rail. In effect, this means that the train starts to be subjected to change when the first bogie passes over the VT, with the forces increasing. This continues until the second bogie crosses the VT, when the forces on the train will be the same. So we can say that the change in cant and radius happened within the distance between the two wheel sets, 12.2 meters. Because of this, it is usual to find the same values of cant either side of a VT, therefore only the Cant deficiency changes. It is rare to find VTs with a change in cant, as it will cause a jerk for the train traveling over it. VTs are treated like any other transition but with a fixed length of 12.2 meters. They are commonly found in S and C layouts, particularly within the switch. And that brings us to the end of this video on railway curves. For more on-track geometry, track design maths or railway engineering in general, please head over to the channel. Thank you for watching our video. We hope you found it informative and engaging. If you enjoyed this video and want to see more like it, be sure to hit the subscribe button and join our community. We have a lot more exciting content on the way, and you won't want to miss a single video.